everyone, and welcome to Activity 17. Today we are starting in your Springboard books on page 241, and you'll definitely want a calculator and pencil to keep track of your notes with and possibly use the calculator. So on page 241, we start talking about dilations. And what I want to bring to your attention before we talk about dilations is the idea of rigid transformations. Remember from earlier this year, rigid transformations preserve the size and the shape of your figure. And we said that the function rule that would describe them would involve just addition and subtraction. So these two would be examples of rigid motions. However, if there's multiplication or division involved, they are non-rigid. Well, that's going to be now the focus with our dilations are these non-rigid motions, because think about when you are on the computer and you are trying to create something either on possibly, Google Slides, for instance, and you're going to try and adjust the shape of something. You're going to make it smaller or possibly larger. That is performing a dilation. And that's what's happening in the examples here is somebody is trying to create a brochure and they're adjusting the size of their shape from layout A to be layout B. So if we look at the coordinates for layout A, we have 0, 0, 0, 8, 6, 8, and 6, 0. And in layout B, still 0, 0, but now it's 0, 4, 3, 4, and 3, 0. So what we're noticing is that we are making the coordinates in layout B half of what they were in layout A. So if we were to write the function rule to describe this, so they are 1/2 of layout A. Our function rule then would be saying, okay, we're taking our coordinates and we are multiplying them by 1/2, or that's the same idea as dividing by 2 to get our new coordinates location. Now, moving on with this idea is we also have example C. And what we notice about example C is that these are even bigger now than they originally were in layout A. So layout A is listed to the left. These are now at 0, 0, 0, 16, 12, 16, and 12, 0. So we're basically taking our original coordinates here, and now we're doubling them in size. So when we double them in size, we would write our function rule as 2x and 2y, since we doubled each of those, okay? So again, this brings back the idea of our scale factor in a dilation. And what a scale factor is, it's the amount in which you are reducing or enlarging. Reductions, like the first example, are when you are decreasing in size. So that was a reduction. But in the second example, we got larger, our shape, so we would call that an enlargement, and the scale factor on that one was 2. Now, in general, your scale factor, what we would call that is the image value divided by the pre-image value. So your final image divided by what it was originally. Something very important that you want to write down, because this is going to help you find the scale factor if it isn't easy to look at, like it would be with just a 1/2 or times 2 reduction or enlargement. So in general, what we would say for a reduction is that our scale factors are going to be between 0 and 1. That's what your scale factor, your K value, is between. So a fractional value a lot of times between 0 and 1. So smaller than 1, bigger than 0. And for our enlargements, on the other hand, we are going to have a scale factor that's bigger than 1. So anything above 1 is going to reduce or be an enlargement. If you're just multiplying by 1, then it's staying the same size, right? And again, we're dealing with multiplication each time. So you're going to multiply each coordinate by your scale factor k. Call that. So each time as a function rule, it would look like this, where we're multiplying k times your x value and k times your y value to either reduce or enlarge. So sometimes what you're going to see is that you're going to have a transformation that's doing two different things. So notice first we have the rigid motion here where we were having a translation moving to the left 4 and down 6, and then we made a scale factor. So what we would do is, again, look at this as two separate pieces. We have to move each of our original coordinates to the left 4 and down 6 to start. So they would actually be at -4, 0, 0, 0, 0, -6, and -4, -6. And then the second piece would be using that scale factor of 1/2. So we're going to take our points now that we just found and multiply each piece by 1/2. So now we're at -2, 0, 0, 0, 0, -3, and -2, -3. Okay. And this would then be your final location after that composition. So we translated first, then we dilated. Looking at number 13, we have another example of a dilation here. Notice this scale factor. Even though it's a fractional value, 5/2 is the same thing as saying 2.5. So this is going to be an enlargement because our k value is bigger than 1. And then if we look down below here, again, just like up above, you're able to create a translation and an enlargement by doing both of these. Now, in this case, it wanted you to dilate first, so you would multiply everything by 2.5 first and then translate it. Okay, and again, if your scale factor is just 1, it's gonna just map it onto itself, right? It's not changing the shape at all, the size at all, because it would just be multiplying by 1, which is going to keep it the same exact figure. Okay. Now, the center of dilation is the point in which you are moving around, right? Now, our center of dilation is always, for this class, going to be the origin. So we don't have to worry about dilating around anything else. But like we said before, with different points of rotation, sometimes you dilate around different things to enlarge it around a specific point or reduce it around a specific point. But all we're dealing with in this class is going to be the origin. Now, to look at some things, again, when we're talking about triangles and looking at dilating with a scale factor, in this case of 2, what we would notice here in each of these is that when you're looking at the side lengths, again, we're doubling these coordinate values, and we would double the length of these sides as well. So we're dilating from the origin, like we talked about, that center of dilation. But what we would see here is that, again, this enlargement shows that the lengths of these sides are also going to be double the lengths of the original sides, just like the coordinates are doubled on that. Okay. And then again, no matter what kind of dilations we are doing, again, if we look back at this example here, whether we're reducing it or we're enlarging it, the shape is not changing at all, just the size is going to be changing. So shape does not change, just the size of the sides when we are completing a dilation. We would also say, though, that the angle measures are preserved, okay? Because you're not changing the shape, so the angles stay the same. But the side lengths will change, right? This is not a rigid transformation because the size changes. So whenever you are performing a dilation, we call this non-rigid. Right. Now, notation when it comes to dilations, we use big D to represent dilation. O represents that we're rotating around the origin, which is what we're always rotating around in this class, and then your scale factor comes next. So if we have a scale factor of 3 in this case, we would say dilation around the origin by our scale factor of 3. So in 23, something that they're talking about with number 23 is an isosceles triangle named XYZ. And they said that the base angle is 65 degrees. And if we dilate this by a factor of 2/3, what would the other measures of the angles be? Well, when we are dilating a triangle or any shape, notice just because we're changing the side lengths, if we're shrinking it, if we're enlarging it, that angle is actually going to stay 65 degrees throughout the whole thing. So the measures of the angles are the same in number 23. And we know that if this is an isosceles triangle, that the base angles are the same, and that the other base angle is 65 then, and then if we subtract from 180, our vertex angle would be 50. So again, they're the same as the original, even after dilating it. And again, if we're going to write, when it comes to function notation, the two notations, we would say one way we could write this is a dilation around the origin by our scale factor of 1/4, or in the other notation, that would look like this again, where you're multiplying by that value. All right, so that concludes 17.1. Thanks for watching. We'll talk more about dilations tomorrow.